Please.
So I will move quickly through it. So my own background, I'm a biomedical engineer. I studied tissue engineering. So I'm well acquainted with the early research behind our product.
Yeah.
So I know that Artelon is newly launched in Asia, but it has been in clinical use now for over 20 years and has been implanted in over 40,000 patients. And we have many studies published on this material, everything from preclinical evidence all the way through long-term level 1 clinical studies, randomized controlled trials. I would like to acknowledge the inventors of this material. Lars Peterson is on the left. Lars is from Gothenburg, Sweden. He's well known for being the inventor of autologous chondrocyte implantation in the knee, or ACI. He did the first human stem cell transplant, published that in 1983. On the biochemistry side, on the right is Per Flodin, who was a part of a team that won a Nobel Prize back in the 1950s. So these two gentlemen invented Artelon in the 1990s as a second generation biomaterial to overcome difficulties that had been experienced with prior materials. The synthetic materials that had been used in the knee before had two main issues. One was that they were not that biocompatible, and the body tended to reject them. And the other was that the mechanical properties did not resemble the body's own tissue. And eventually you had stress shielding and device failure. So the material that they invented is a polymer-based textile. So we make the polymer, and then we make it into fibers, and then they knit it into a textile. This is a medical device. It's sterile packaged. Has a 5-year shelf life and can be stored in any conditions, doesn't need to be kept frozen or anything for transportation. It's very inert biologically, very strong, and very elastic, like your body's own ligament tissue. You can see in the video there, I hope that it's working, that the material has some stretch to it and can give and stretch like a normal ligament, but it's creep resistant. It always recovers its shape and comes back to its normal position. So we have both bands made of this material, long skinny strips, as well as patches, as you see in the photographs. So the three main characteristics that we talk about with Artelon, we call it the 3 R's. So the first one is that it restores kinematics around the knee. Because it has mechanical properties that resemble normal tissue. The second one is that it resists necrosis that autografts and allografts are subject to. When you use a biological graft, in the early period following surgery, the body must break those grafts down and eliminate them so that a new tissue can form, and those grafts get much weaker during that early healing. And it also is very benign, Artelon. It's less inflammatory than titanium, than polystyrene. The third R is regeneration. Because the mechanics are being transmitted through the tissue, and because it scaffolds new tissue growth, Artelon permits new replacement tissue to grow in its place, and then eventually it dissolves and goes away. So just very quickly, a summary of some of the evidence available. In the United States, there's a very high burden of proof for these materials. The Food and Drug Administration has a guidance document that dictates the sequence of evidence required to bring a product like this to market. And the Artelon completed all of these requirements to bring this to market in the US as a ligament augmentation material. So when we talk about preclinical evidence, animal studies, the first study they did was just biocompatibility. And they found that the material was less reactive than titanium, than polystyrene, did not cause proliferation of scar tissue or disorganized tissue, and that in the healing cascade, there was a very rapid transition to the reparative phase of tissue healing. And the material integrated quite well, was not encapsulated or separated from the surrounding tissue. This is the biggest preclinical study that we did. There were 3 separate animal studies that were done. The first was biocompatibility in rabbits and guinea pigs. The second was function and histology in rabbits. The third was function and histology in pigs. Those were followed for 2 years after surgery. And what they found was that it confirmed their design requirements, that the stiffness and elasticity were similar to native tissue, that the devices had very good strength, very good fatigue life, didn't have creep. There was no systemic reaction to the material. They were not able to find Artelon elsewhere in the body after these studies. And the histology was quite good following implantation. The animals that had it had very good knee function. There was no discomfort or instability. Very quickly, this is 1 week after implantation, and I'm sorry if the slide is a little confusing. So on the left, you have Artelon. On the right, you have vicryl suture, so resorbable suture, and this is a comparison between the two. So when you look at the suture on the right, you can see that even 1 week after implantation, the animal has begun to encapsulate it. It's building a wall around that suture to wall it off. The red dots are immune cells. Those are macrophages. And it's recognized that as a foreign body, started to attack it, degrade it. On the left, you have Artelon. And you can see that those immune cells are evenly distributed throughout the tissue. They're not attacking the Artelon fiber. And you can see that the blue collagen is already integrated to the Artelon fiber. It's adherent to the surface, and the tissue is growing onto that fiber. So this is good. This is what you want. This is at 6 months, and now you see the white Artelon fibers continue to be well integrated in the ligament. You see new vascular channels in red. These are capillaries bringing new blood and nutrition to the tissue. And this is at 3 years. You can see that the Artelon has begun to dissolve. I'm sorry, it's at 2 years. You see bands of completely new ligament tissue within the Artelon that are organized and have good histology. They're fibrillated and wavy like normal ligament. The fibroblasts within that tissue are elongated. These are happy cells. So it's a very good result in the preclinical work. From there, they went to a human clinical trial. So this was executed in Sweden with Lars Peterson and 4 other centers, so 5 centers in total. They studied over 200 patients, and they followed them for 12 years. The 2 groups in the study, one was patellar tendon autograft, and the other was patellar tendon autograft that was augmented with Artelon. So what they found was that the 2 groups were equivalent in terms of safety and efficacy over the course of the study. The Artelon devices had survivorship of 90% at 12 years, so very good survivorship of those surgeries. No increased incidence of adverse events or reactions in the Artelon group as compared to the gold standard, patellar tendon. And they found trends towards superiority with the Artelon. Despite the fact that they had some early technical failures, in the Artelon group, they had difficulties with the interference screws in the femur, and they lost fixation in the first 6 patients. And even despite that, the groups were similar in terms of safety. If you stratify those patients out, the Artelon patients actually were superior. And those patients had better knee stability, were better in the functional outcomes, had earlier return to play, had longer playing careers, and had slower progression towards arthritis, all the way out to 12 years. There's another study that was completed in Italy that is not yet published, and I think this may be covered later today, but this was a consecutive series of 62 professional athletes. They augmented Artelon with a hamstring autograft, and they followed the patients out to 5 years, although now they have data out to 8 years, and they took a number of functional and subjective scores. And they found that these players returned to play in an average of 5.5 months, 80% of them at the same level of competition. They had no major adverse events, no device failures, no removals. The patients reported excellent functional subjective outcomes, and they did not observe any arthritis out to 8 years now. And then this is the last piece of evidence that I want to talk about. Over the course of time, we have had the opportunity to biopsy Artelon out of a number of patients. So this is reporting on 21 different human subjects that had Artelon biopsied out of them. The graph is a little difficult to understand. So the red sequence of dots is an in vitro study where they just took Artelon and put it in water at 37 degrees C and let the Artelon dissolve over time in water. The black data points, each of those is an individual human subject that had a biopsy at a point in time from 1 to 6 years after the operation. And they found that the rate of degradation of Artelon in vivo in humans was exactly the same as if it was just in a bath of water. So the conclusion was that there is no additional immune response to Artelon that's accelerating the breakdown of this material. It dissolves in your body the same way that it dissolves in a bath of water while new tissue is being built. So to conclude, there's been a lot of evidence on this. I've reported on just a small amount of the evidence that's available. But back in the 1980s and 1990s, there were a number of biomaterials that failed in these same studies because either they weren't biocompatible or they had poor mechanical properties. During that time, allografts and autografts became popular and became the standard, certainly here in the United States. But what we found recently is that allografts also have reported generally poor outcomes in ACL augmentation. So there's still an unmet need in the market. And the evidence that we have for Artelon at this point is that it's proven to overcome the shortcomings, both of the first generation biomaterials and the allografts that have been used in their place, by restoring kinematics, by resisting necrosis, and by regenerating new tissue and eventually dissolving and going away.